Bonjour. I am Louise Ferguson. I am a horticulturist from University of Davis at California. My specialties are alternate bearing, salinity management, mechanical pruning, and mechanical harvesting, particularly of olives and rootstocks. My crops are pistachios, olives, citrus, figs, persimmons, pomegranates. I've been asked to tell you what's new in California and also to focus on our major problems. So our major problem, let's see, where should I stand here? Our major problem actually in California are many just like yours, but first I'm going to tell you a little bit about the California industry. We have about 100,000 hectares of citrus in California, how do I make it go back? Where's the pointer? Is this the pointer? Make it go back. Yeah. That's the pointer. About 50% of our industry is navels and sweet oranges. Another 20% is mandarins. Another 8 to 12% is lemons, Lisbon and Eureka. And then we have a few limes and a few pomelos and a little bit of grapefruit. Overall, the citrus industry has been maintained rather steadily. We are dropping slightly in increasing slightly in acreage, but the navels and the Valencia-bearing acreage is decreasing. Lemons are very steady for us, Lisbon and Eureka. The big news in California is that the mandarin-bearing acres are increasing, and interestingly enough, the grapefruit just slightly. Okay? We have 3 distinct production regions in California. I want to point out that the Central Valley here is an old inland seabed. It has no subsurface drainage to the sea. Therefore, every bit of fertilizer we pour on the Central Valley stays in the Central Valley because there is no, even with this outlet, there's no subsurface drainage to the sea. Salinity is becoming a major problem for a number of crops. But basically, the 8% of our lemons are grown here in the coastal regions in the green. They are primarily the Eureka. Out here in the desert is where we have our grapefruits and our Lisbon lemons. And the San Joaquin Valley, primarily the southern half of it, is where approximately 75% of our oranges, mandarins, and navel oranges are grown. Okay, just to give you an idea of our production and value, California produced 4.15 million short tons of citrus, worth about $2.5 billion in 23-24. We produced 79% of the total U.S. citrus production. We're 6th in the world for citrus production. Brazil, China, the European Union, now that they lump the countries, Mexico and Egypt are ahead of us. We sell about 70% domestically. We export about 30%, primarily to the Southeastern Asian countries and Australia. Our total production did increase in 24 to about 4.75 million boxes. A box is about 18 kilos. So that's about a 7% increase in orange production. The big news is the mandarins and tangerines increased about 17%. Lemon production and grapefruit production both decreased. But in terms of value, all of them increased, but particularly the mandarins and the lemons. Okay. So let's talk about our problems. Just like you, we're a Mediterranean climate, except I think we have maybe more severe salinity problems. We have, of course, our major pests and diseases. We have the threat of Honglong-Bing. We have active quarantine monitoring problems for ACP. Honglong-Bing is primarily, it's thus far, officially, it's only in a few commercial orchards. Our big problems are what we call our backyard trees, the trees in people's homes. Just like you, we have problems of climate change and water scarcity. and increasing temperatures and decreased water quality and quantity. You know, because the San Joaquin is in Central Valley is an old inland seabed, our problems are primarily sodium chloride and the element boron. We, of course, have labor shortages and immigration issues, and our market competitors are primarily Mexico, Spain, South Africa. So our larger industry problems are the same as yours. But our major production problem is one that we can address. California, for a state that was built on water, has very poor water management until the recent decade. And right now we're having problems with our growers in terms of nitrogen and irrigation management. Generally, the growers are applying excessive nitrogen, which results in overly vigorous trees. This means we have more susceptibility to insect pests, and because the canopies are thicker, more humid, and the trees are more succulent, the leaves are more succulent in the fruit, and a botrospharia problem. And of course, decreasing peel quality, delayed coloring, regreening. But the larger problem in California is that this excessive nitrogen application is leading to groundwater contamination, particularly in the form of nitrate contamination for drinking wells. We have developed two very strong regulatory programs. The Irrigated Lands Regulatory Program. Farmers must report their nitrogen application rates, their crop harvest to tell how much has left the farm, and on-farm wells must be monitored. The SGMA, Sustainable Groundwater Management Act, they have to implement groundwater sustainability plans to avoid contamination. It's not moving. Little thing's not working. Where's the AV? Can you advance the slide back there, and I'll just wave my hand when I want one advanced? There we go. Okay.
Where? Press on here to advance and here to go back.
Oh, yeah, it wasn't working. I pressed and pressed. Okay, just to show you why and how it's becoming a problem. The pointer's working. Basically, we all know how we get nitrogen into the soil. It's with our irrigation water. We're hoping it goes over here, it stays in the wetted root zone and in the available water content, and that the nitrogen and water, of course, move up the tree and facilitate photosynthesis, and the removal of nitrogen with harvest. This is not a great loss. This is our problem, because nitrogen, regardless of the form you put it on the soil or how you apply it or how you irrigate, it very quickly turns to nitrate. And if you do not irrigate properly, percolates down to the water table and becomes nitrate contamination. Okay? So let's talk about how bad these problems are. In the Irrigated Lands Regulatory Program, which covers the entire San Joaquin Valley, this old seabed, only certified crop advisors or growers with training can write nitrogen fertilization programs. All growers must maintain complete records of their plan to fertilize, how much they put on, how much was already there, how much is in the water. They have to have their pre-season soil nitrogen. That means another set of lab tests for every representative piece of ground. They have to document the removal of yield and harvest, and they have to show that they implemented plans. At the end of the season, the records will be tabulated and the nitrogen ratio calculated, basically the efficiency of the nitrogen, and all outliers will be notified and an implementation plan will be put in place. Okay? And of course, we know the effects on a citrus tree. The citrus tree becomes much more susceptible to mealybug, the aphids, the scale insects, and the disease botrospharia, which is new for us. It was previously known as Dothiurella ergomosis. And fruit quality, thicker, coarser peels, delayed coloring, regreening, and staining in navels. Okay? So I'm going to tell you a little bit of research now. that we did to try and see if we could do something to increase what is the nitrogen use efficiency in nitrogen applications. Generally, it's considered in the United States about half the nitrogen you apply is lost. It's not used. Go back one. For both navels and mandarins, we first did a survey of our growers, thousands of acres. We asked, how much are you applying in pounds per acre? Pounds per acre to kilos per hectare, 1.112 multiplier. So most of our growers were starting at about 75 to 100 for the navels and putting on up to 150 pounds to the acre. That's about 170, 180 kilos per hectare. Okay, if you go over here and you look at the same set of nitrogen applications and have yield as a function of nitrogen application, you can very quickly see that at 75 to 100 pounds per acre, it's about 85, 90 kilos per hectare, you get very little increase in average yield all the way up to about almost 200 kilos per hectare. So even though a lot more nitrogen is being put on, it's very inefficient. You're not getting an increase in yield. If you look at the situation in which applied is divided by the nitrogen removed with the fruit, you very quickly find that would be, if you applied 1 kilo and it took away 1 kilo, that ratio would be 1. What you can very quickly see is that's reached at 25 to 75, that's about 80 kilos of nitrogen per hectare. The rest of it is lost. And that's reflected over here with applied minus that removed. The value for that, of course, would be if you applied a pound or removed a pound, the value of perfection would be 0. And you can see that is very quickly reached at about 80 to 90 kilos per hectare, and the rest is lost. Very similar story for mandarins, except that their application rates are a little higher, getting up almost 250 pounds to the acre. That's about 300 kilos to the hectare. And a very similar story. After about 90 kilos per hectare, very little increase in yield. Certainly doesn't justify the cost of the nitrogen and the labor. Same story, perfect value of 1 is reached here very early, 50 to 75 pound, about 80 kilos to the hectare, and nitrogen is steadily lost when you plot the nitrogen applied versus removed as a function of yield. Okay? Oh. So we did a nitrogen rate study for about 3 years. We did navels and mandarins, multiple field plots, mature trees with good productivity. We went high on the values. We used easily infiltrated forms, calcium ammonium nitrate 17 and urea ammonium nitrate 30, UN32. We applied it in all the fertigations. We collected leaf and fruit samples from several individual trees several times during the season, and all the trees were individually harvested during the season at the end. Our goal was to develop a nutrient demand curve to guide the quality and time of fertilizer application. Here is this is a stretch of about 200 miles. I'm bad with kilometers, but excuse me, about a stretch of about 150 miles, so maybe 250 kilometers. We had different varieties, different ages, different tree spacings, different nitrogen application rates, and over 50 orchards and 1,000 plus trees per orchard. Okay? We determined the annual nitrogen removal by collecting anything that grew that year, plus measuring the harvest. We determined the nutrient demand in the growth of the tree by, at the end of the 3 years, excavating, partitioning, and analyzing the perennial growth. And this is what we came up with for an annual dynamic of application and removal. Basically, early in the spring, when it's nothing but vegetative growth, prior to bloom, oh, I should explain this. This is time on this axis, and this is nitrogen pounds per acre, okay? Removed. The green part of the bar is the perennial parts of the tree. The red part of the bar is the leaves, the blue is the fruit. So those two separate sets of removals that you saw in the harvest are what generated these bars. And what we came up with through the season was early in the season, March, April, bloom, and up till fruit set, no removal by the fruit. And very steady maintenance of what's in the tree and what's in the canopy. But as you went through the season, basically what you saw was more and more nitrogen partitioning into the fruit. Yield accounted for 50 to 80% of the total demand, and demand usually stopped by October. You can see there's very little increase there. Okay. This is another way to look at it. Basically, this was in the mandarin plot, and basically what we found here is really by September, October, 80% of that nitrogen was into the fruits, very little picked up afterwards. And what we used this to do was to estimate yield and to develop a fertilization plan for the following season. So basically what we're starting to do in California is leaf analysis from a non-fruiting branch in August is not that important to us anymore. Leaf analysis is a little too late for us. Basically based on the previous year's yield and the nitrogen residual in the tree, we are designing the nitrogen program for the following year. Okay? And here's what we came up with in terms of total demand. For the fruit, the nitrogen accumulation occurred rapidly early in the season. 90 to 80% of the total nitrogen in the fruit was in there by September, October for both navels and mandarins. We found that for every 1.5 kilos of fruit, every 1,000 pounds of fruit, 1.5 kilos of nitrogen was removed. For mandarins, the offtake was 1.3 pounds per every 1.3 kilos for every 1,000 kilos of fruit. For the perennial nitrogen, the nitrogen that went into the growth of the tree, the nitrogen accumulation was rapid till the end of August in both species, navel and mandarins, while continued later with a lower rate. The low net accumulation of nitrogen after late October we observed a low accumulation of nitrogen in late October. From December to February, the amounts of nitrogen in the tree canopy remained steady. The tree only used about 0.15 pound, I can't translate that to a kilo, of nitrogen per tree per season. So those are the figures we based our fertilization programs on. Okay, so this is how we design a fertilization program. Say we have 200 trees per acre based on what we know about the yield patterns of a mature orchard. We calculated, say, in this case, there was 30,000 pounds of fruit in that acre at 200 trees to the acre. That would be, what, 500 trees to the hectare? We multiply the expected yield, which is an estimate by an experienced grower, times the fruit removal figure, which in a case of 30,000 pounds of fruit would be about 45 pounds of nitrogen per acre. Multiply that times 1.12 to get kilos to the hectare. That will be about 50 to 60 kilos to the hectare. The biomass, the tree accumulation, was only 0.15 pounds, and that would, in the case of this, amount to 30 pounds of nitrogen. So our total fruit biomass would remove about 75 pounds of nitrogen per acre, or, I did translate it here, 84 kilos per hectare. Then you have to decide, based on your records, your nitrogen uptake efficiency. If you apply 75 pounds, only half of it taken up, then you put on 150 pounds or 168 kilos per hectare. If you think you can get 70% efficiency, that's 110 pounds of the acre or 124 kilos. Okay? Where does nitrogen uptake occur? We did root measurements, but basically what we found was most of the roots were in the top 45 centimeters of the soil when we pulled it out. We demonstrated it by counting the roots. This one is actually in centimeters. I got good on this one. And that's about the top 18 inches or first half meter of soil. So this is where your irrigation program comes in. In California, we are almost exclusively drip, sometimes sprinkle irrigation, but basically we try to keep the top half meter of the soil wetted for efficient fertilization. We irrigate by ET, evapotranspiration, generally, and use a crop coefficient of about 0.55, 0.75. Okay, so this is how we teach our growers. With that 1.5 pounds of 1.5 kilos per 1,000 kilos, and 1.3 pounds per 1,000 kilos of fruit they think you're going to remove, plus a little bit for the tree. We encourage them to put it on before fruit set, and in the following 4 months in as many irrigations as they can manage to refill the profile directed by ET, and diminish it from August through mid-October and nothing past. Irrigation, I'll be showing you some tools in the next part of the talk, but we basically irrigate by evapotranspiration and crop coefficient. It's the major method, and we do use highly efficient sprinkler irrigation systems, about 90 to 95%. With this system, when we tried it, we got about 80% nitrogen use efficiency. Okay. Like I said, leaf sampling, it's coming too late for correction. It's not used much. And basically what we've found in multiple crops is that fruiting and non-fruiting branches, we get big differences in content, even within a tree and even within, not so much, within canopy for both potassium and nitrogen. So we're moving away from using leaf sampling as directing our fertilization programs and moving toward more budgeting for nitrogen use efficiency based on crop load. Okay, now I was told you wanted to hear about some of the newer technologies in California. I'm only going to talk about the ones that we are now implementing, okay? So just as the previous speaker talked about Landsat and GIS, we are starting to develop statewide land use monitoring with GIS and remote methods. We're starting to use aerial monitoring, primarily from planes with high altitude for determining the health of a grove and predicting if it's going to have a steady healthiness. That's a better way to put it. And we often, this is usually airplane monitoring. We do monitoring with small drones, but the problem with small drones is they can't contain many they can't take the heavy load of many spectral lenses and are of limited use. They're best just for size. I would recommend most people get their own drone and run it frequently, but it can't tell you much more than size. And we often, our high altitude monitoring, we synchronize it with stem water potentials as a ground truthing for water stress. We're moving more to plant-based monitoring with leaf, fruit, and trunk sensors, having mixed results with those. And of course, stem water potential for directing irrigation, it's nothing new. Stem water potential was around when I was in grad school 40 years ago. But back then it was a research tool. Now it's an irrigation company tool. We're starting to move toward more integrated systems where there'll be a transducer on the irrigation line so you know what was delivered. There'll be an indwelling soil sensor, both conductance and capacitance for available water content and for salinity management. They're not as, even the best indwelling sensors like the Sentex from Australia, what we found are they're not good for an actual salinity measurement. They're better for which way the salinity is going, but for giving you an actual decisiemens per meter, we haven't found it very good. And then trunk transducers to show the shrink
Excuse
in
me,
soil.
Dr. Louise, if
Almost-
you still have 3 minutes.
3 minutes,
If
I
you
can do this.
conclude.
And now we're starting to move to online decision platforms for chill and heat accumulation and something called crop management. Now I'm going to show you pictures of all these. Okay, Land IQ. This is the cumulative, this is a remote sensing GIS system that we use for all kinds of different measurements to show us consumptive estimation, landscape evaluations. This is the kind of thing it can give us. Land IQ can tell us where all the pistachios are grown in California. I didn't have a citrus figure. But we're basically using these large Landsat systems to tell us what's going on, both soil, water, crop-wise, and other things. Okay? This is aerial monitoring. This is a salinity plot of mine where I had really different soil profiles, but basically it can give me the NDVI, the measure of vigor in my trees, the measure of stress, growth of the canopy, chlorophyll content. Here you can see that this part of the plot is more stressed than this one when I give it the normalized differential vegetative index. There we are, and here's normalized. So basically, these aerial management, or these aerial flyover tools can give you a good status of your whole orchard and determine bad patterns with it. We've got a whole panoply of sensors coming out, having differential results with them. Here's a leaf monitor for basically leaf water stress. Here's a little fruit monitor for fruit growth. Here's basically a trunk transducer. Here's something, this sensor we can use for bark heat because we're very interested in is the solar irradiation heating up the bark more than the bud in the winter for increasing bloom, okay? And of course, this is probably our major tool, basically a pressure chamber that gives us tree water status. We used to do them pre-dawns, but now we have moved to high noon by just wrapping the leaves up. But basically, this is the tool that is used most now for determining irrigations. We do not use the neutron probe as much. It's just too heavy and too dangerous. Stem water potentials can be done much more easily. Okay. Here's a dendrometer that gives you the shrink and swell of your trunk and shows you if your trunk is growing steadily. There's the trunk shrinking during the day, and there's the trunk expanding at night. Okay? We're starting to move to much more integrated systems. This is a salinity experiment that I had in pistachios, where I was testing the ability of single and double lines delivering the same amount of water in the same amount of time to see which could most effectively leach the sodium and the chloride and the boron out of the soil. What I did was sink a Centec probe at each of these locations away from the irrigation hose so I could follow the pattern of the available wetted zone and the pattern of the salinity. There was a transducer on the trunk and a transducer on the line, so I knew what I delivered, I knew how the trunk was responding, and then we did aerial flyovers. Basically, we found the double line was better for leaching salts. Okay. This is the kind of output I got from the sensors. This line is the available water content, and this is the infiltration map. So these integrated systems are kind of fussy, and they're very expensive, and I'm not sure of the value of them yet. Okay? And another thing we're starting to do, we aren't doing it in citrus, so I'm showing you my pistachio work, but the pistachio industry has been as big a success in California as the mandarins, and we were doing farming by calendar date, but about 10 years ago I started doing it as a function of growing degree days. because pistachios have a very peculiar pattern. First, they grow the shell. That's called stage 1. Then they fill the shell. That's called stage 2 and 3. And then they ripen. So basically, based on the growing degree days, I don't want to stress the tree for water up here to 1,000 to 1,200 hours, because the size of that shell is going to determine the size of my nut at harvest. However, there's a short period in here where nothing is happening for about 500 hours. I can cut the irrigation back 25%. But when this nut starts to grow, because strangely enough, it's the pressure of the nut pushing the shell that splits the pistachio and makes it valuable, I again do not want to stress the plant for water. So basically what we're starting to do in California is we're starting, instead of calendar dates, we are starting to use what we call decision support tools. I'll tell the grower, all right, about 800 hours, you should be going out and looking and seeing if you've got maximum shell size. Or about 3,500 hours, you should start to go out and see if your hulls are starting to slip and your shells are starting to split. We don't call these calculators, we call them decision support tools. When you approach the stage where something is supposed to happen, the grower is supposed to go out and look and see if it's really happening. He's supposed to verify it. And then we have some really major online decision support tools that require quite a bit of input. This is Crop Manage. This is where you find it. It uses all the inputs, including the land satellites, the soil and water maps, the form of fertilizer, the volume of irrigation water, the quantity and quality of the water, basically the structural and chemical aspects of the soil, all entered here, and again is the decision support tool for managing your nutrient and your irrigation programs, but it integrates all those inputs that we now have that we have found are usable. And I think I made it to the end.
Thank you very much.